Welcome to the next module. So, in this module and in the next module, we are going to discuss the concept of hyperelasticity. We will develop the necessary equations and linearization associated with hyperelastic material. Okay. So, the contents for this module are as follows. So, we will first look into what is meant by constitutive relations. Okay. And then, since this is not a course on continuum mechanics, so we have left out what is called thermodynamics part. Okay. So, we have to actually cover certain topics, okay, so that we have a background on what is necessary to get certain constitutive relations. Okay. So, one type of constitutive relations that we are going to discuss in this particular course is on hyperelasticity, but we will look into what are the certain constraints that are enforced on the constitutive relations because of the thermodynamic considerations, okay, and there are some other consideration like objectivity. Okay. And then once we have dealt with the constraints on constitutive equations, we will go into introduction to hyperelasticity. Okay. We will look into what is meant by hyperelastic material, okay. And then we will derive the material or the Lagrangian elasticity tensor followed by the spatial or the Eulerian elasticity tensor. Okay. So, these tensors will be necessary when we are going to linearize our virtual work principle, okay, which we discussed in the previous lectures, and there these concepts will be helpful. Okay. So, let us begin. So, in our previous modules on kinematics and kinetics, we had explored the physical laws that govern the behavior of the continuum system. Okay. So, these physical laws resulted in a set of partial differential equations which were expressed in the deformed configurations. Okay. What were these equations? So, the first equation was the conservation of mass. So, it was given by the material time derivative of the density plus the density times the divergence of the velocity field equal to 0. This is essentially the spatial form of the conservation of mass. Okay. So, the material form was rho 0 equal to rho j. Okay. So, that was the material form and this is the spatial form. So, this is one equation, okay, which is in the density rho. Okay. So, next we had discussed balance of linear momentum and this led to the equation of motion, okay, divergence of the Cauchy stress tensor plus the body forces equal to rho times the acceleration. Okay. For static problems, the acceleration part goes away and then what you get is the equilibrium equation, divergence of the Cauchy stress tensor plus the body forces equal to 0. So, these were essentially 3 equations. Okay. So, you had 3 equations and this part we did not cover because this is not a course on continuum mechanics, but if we look into the thermodynamics part, there the conservation of energy, okay, leads to, or the first law of thermodynamics leads to following equation. So, this is one equation. Okay. So, you have the internal energy plus the rate of generation of heat inside the body minus the external heat flux should be equal to the rate of change of internal energy. Okay. So, that was one equation if you come from the thermodynamics aspect. Okay. So, along with this you had balance of angular momentum which were 3 equations which basically resulted in the symmetry of the Cauchy stress tensor. Okay. And then the second law of thermodynamics led to one equation where the rate of change of entropy S dot, okay, is given by following expression. Okay. So, these are basically the equality and inequality equations. Okay. So, essentially the last two are not governing equations, but they are rather constraint on the continuum systems. Okay. So, these equations are not equations per se, but they are rather like a constraint on the continuum system. Okay. So, a continuum thermodynamical system is governed by 5 differential equations, okay, which are called the field equations. Okay. So, you had one equation over here, you had 3 equation over here, and you had one equation over here. All in all, you had total of 5 equations, and these 5 equations are called the field equations or the governing equations. Okay. Now, let us see how many unknowns we have. Okay. So, the total number of unknowns that we have is, one is density, there are 6 stresses, then you have the internal energy, you have the temperature, you have the positions, you have the heat flux, and you have the entropy. Okay. If you count total 1 plus 6 plus 1 plus 1 plus 3 plus 3 plus 1. So, all in all this gives you total of 16 unknowns. Okay. But you have only 5 equations to solve for. Okay. So, you have 16 unknowns, but you have only 5 equations to solve for. So, to accurately or to precisely solve these equations, okay, we need some extra set of equations. Okay. So, we have certain missing relations, and these relations are obtained, okay, when we set up our constitutive relations, okay, which are also called the response equations. Okay. So, what are constitutive relations? Constitutive relations describe the response of the material to the mechanical and thermal loading which are imposed on the system. Okay. So, when we describe the constitutive relation, we will get the extra 11 equations which will help us to solve for these 16 unknowns. Okay. Now, we need the constitutive relations for internal energy, temperature, stress, and the heat flux. Okay. So, in general we will need these many. Okay. So, we will need 6 equations over here, you will need 2 equations over here, and you need 3 equations over here. Okay. So, 6 plus 3 plus 2 equal to 11. So, these 11 equations, okay, when we get combined with the previous 5 field equations, will result in the solution. But in this course, we are only dealing with isothermal cases. Okay. There are no heat flux into the system. Okay. So, in our case only the stresses will be unknown. Okay. Now, these constitutive equations or the relations cannot be selected arbitrarily. Okay. So, they must conform to certain constraints imposed of them by the physical laws, and they must be consistent with the structure of the material. Okay. So, you can just cannot select any constitutive relation. Those constitutive relations cannot be arbitrary. They have to be selected based on certain constraint which are imposed by the physical laws, and also the constitutive relations must be consistent with the material that you are having. Okay. So, all this that we are covering right now is for the sake of completeness. Okay. So, also these constraints help us to greatly reduce the set of possible forms from which all the constitutive relation must be chosen. Okay. So, there are many forms you can choose, and with the help of these constraints you will be able to narrow down on certain possible forms only. Okay. So, the objective of these constraints, okay, is to derive the restriction on the possible functional forms on the constitutive relations, and the constitutive laws or the relations are assumed to be governed by the following fundamental principles, okay, which are the principle of determinism, principle of local action, restrictions which are imposed by the second law of thermodynamics, principle of material frame indifference, that is objectivity. This we have already seen what is meant by objectivity, the material symmetry, and for example, additional constraints can be material without memory and without aging, and materials whose internal energy depends solely on the entropy and deformation gradients. Okay. These are some of the other constraints that you can consider, and based on these constraints you can derive the constitutive relations. Okay. So, we will look one by one into all these constraints in mostly one slide to complete our understanding on the constraints imposed on the constitutive relation. Now, the first principle is the principle of determinism, okay, and this is the fundamental philosophical statement at the heart of science that proposes that the past events determine the present. Okay. So, what it means is, if you know the past deformation of the body or the continuum system, it should be possible to determine the current configuration of the body. If you know everything about the past, it should be possible to tell about the present. So, this is called the principle of determinism. Okay. Say for example, the stress at a material point x in a body at time t can be determined from the history of motion of the body. Say for example, its temperature history and so on. Okay. So, as I have written here, the stress at a point material point x at time t is a function of its deformation mapping, say the temperature, and there may be many other variables, and say its current position explicitly, and also explicitly it can depend on time. So, if you look closely, there is a superscript t here, okay, which denotes that these quantities psi, t, x, they are dependent on the history. Okay. So, time t means you have known these quantities from the time t equal to 0 when the process actually started. Okay. So, that is what denotes the, this t denotes the history. Okay. So, a material that depends on the past as well as the present is called the material with memory. Okay. And the explicit dependence of this function f on x, you see this f depends explicitly on x here, okay, that is the material coordinate x. So, this allows for the what is called heterogeneous materials, where the constitutive relations can be different in different parts of the body. Okay. So, explicit dependence on x is for heterogeneity, and the explicit dependence on time t allows for the response of the material to change with time to account for material aging. Okay. You might have come across material which over the period of time, okay, if you do not apply, you apply stress and leave it there, after a certain period of time they will develop cracks, they will deform in a certain way. Okay. So, the material is said to be aged. Okay. So, this explicit dependence on time t is for material aging. Okay. So, this statement for example says that from principle of determination that the stress at any material point x at time t can be determined if you know all these. Okay. So, it can be determined if you know the history of all these variables. Okay. Now, there is a principle of local action which states that the material response at a point depends only on the conditions within an arbitrary small region around that point. Okay. So, if you look closely, psi here was not considered a function of x. But now, from the principle of local action, okay, the same relation that we had in the previous slide is now dependent, okay, all the variables are now local. Okay. Local means they are all pertaining to the material point x. Okay. So, psi corresponds to material point x, it does not correspond to any other material point. Temperature corresponds to the current material point, okay, like that. Okay. So, now if your material has no memory, what it means? It means that there is no, so this time dependence which was here goes away, you see there is no time dependence here, okay, it goes away. So, if your material does not have memory, so it means it does not know the past, it only knows the present, which means that psi, the deformation mapping, psi, temperature and all such quantities only correspond to the current position, okay, at current time t. Okay. Such materials have no memory. So, example of such a model is the generalized Hooke's law for hyperelastic material under conditions of infinitesimal deformation, where the stress is a linear function of small strain tensor at a point. Okay. So, sigma ij is Cij KL epsilon KL, which is the standard Hooke's law, generalized Hooke's law, and all the stresses, the material constitutive tensor C and the strain, they all depend on x, that is the particle of interest. For example, strain is at that particular point, the strain is not obtained from strains of some other points. Okay. So, one point to note is this principle is not universally accepted. Okay. For example, in non-local continuum theories like the Ehringen's non-local continuum theory, the Schlick's peridynamic theory, okay, the stress at a point is considered to be computed using an influence zone. Okay. So, rather than sigma here, for example, being computed based on only at point x, sigma will be computed based on a certain influence zone. Okay. So, we discuss no further on this, but the principle of local action is not universal. Okay. Now, coming to the second law of restrictions. Okay. So, constitutive equation cannot violate the second law of thermodynamics, and so second law of thermodynamics states that the entropy of an isolated system remains constant for a reversible process and increases for a irreversible process. Okay. So, for example, a constitutive model for heat flux must ensure that the heat flows from hot to cold region and not vice versa. Okay. So, if you are proposing a constitutive relation for heat flow inside a material, okay, then your constitutive relation for heat flux should be such that it should always result in flow of heat from the hotter regions to the colder region, because heat cannot flow from cold to hot region. So, any constitutive relation, okay, or the model for heat flux which shows the opposite, that is flow of heat from the cold to the hot region, will not be accepted, because it violates the second law of thermodynamics. Okay. So, the second law of thermodynamics takes the form of Clausius-Duhem inequality. Okay. And the application of this inequality to impose constraints on the form of constitutive relations was pioneered in the 1963 paper by Coleman and Knoll. Okay. So, this is that paper. For the sake of completeness, I will given it here. Okay. So, the approach that was outlined in this paper is called the Coleman-Knoll procedure. Okay. There are other procedure, for example, the Liu procedure, which is given in this paper, other than Coleman-Knoll procedure, to apply this kind of second law of thermodynamic constraint. Okay. Now, the next constraint is the principle of material frame indifference or the objectivity criteria. Okay. So, all the physical variables for which the constitutive relations are required must be objective tensors. Okay. So, an objective tensor is a tensor which physically remains the same in all frames of reference. For example, the relative position between two physical points is an objective tensor, whereas the velocity of a physical point is not an objective, since it will change depending on the frame of reference in which it is measured. Okay. So, the condition of objectivity imposes certain constraints on the functional form of constitutive relation, which ensures that the resulting variables are objective or material frame indifferent. Okay. So, the objectivity criteria or the principle of material frame indifference will impose certain constraint. Okay. So, in our hyperelastic constitutive relations, we will see what kind of constraint is imposed by principle of material frame indifference. Okay. We will come to it in next few slides. Okay. Next comes the material symmetry. Okay. So, the constitutive relations must respect any symmetries that the material possesses. Okay. So, for example, the stress in a uniformly strained homogeneous isotropic material, that is a material that has the same mechanical properties in all directions at all points, should be the same regardless of how the material is oriented before the load is applied. Okay. So, our isotropic material has this kind of symmetry. Okay. So, if you take different specimens and then if you load them, the response with the same force in the same direction, it does not depend, the response of the material will not depend on how the two materials were oriented before the forces were applied. If you apply the force in x direction, the response of the material will be same for both the samples, because it has that symmetry built into it. So, your constitutive relation which will describe this kind of material behavior, that is the isotropic material behavior, should be respected. Okay. The other is the materials without memory and without aging. Okay. So, if you have this restriction in place, which means that along with the principle of local action, the constitutive relations for internal energy, temperature and stress and the heat flux only depend on the local values of the state variables, okay, and their time rates of change. Okay. And materials whose internal energy depends solely on the entropy and deformation gradient. Okay. So, for this, the possibility of the constitutive relation depending on any rates of deformation as well as higher order gradients on the deformation will be excluded. So, these are certain. So, the last two constraints are very specific, but the first 5 are usually the constraint which have to be respected. The other 2 here are the constraints which are specific. So, if you have a specific kind of material, these constraints have to be respected. Okay. With these kind of constraints, one can derive the constitutive relation. Because this is not a course on continuum mechanics, we will directly deal with our hyperelastic material, for which all these constraints are already satisfied. Okay. So, material for which the constitutive behavior is only a function of the current state of deformation is known as a simple material. Okay. So, what is a simple material? Its current state is a function of current deformation. And now, a simple material without memory is called a simple elastic material. Okay. So, if the material does not have any memory and its state depends, the constitutive behavior of the material depends only on the current state of deformation, then that material will be called a simple elastic material. Okay. So, under these conditions, the stress at a material point x is a function of the current deformation gradient f associated with that particular particle. Okay. And since the deformation gradient tensor f is the work conjugate with the first Pala-Kirchhoff stress tensor. Okay. So, the elasticity can be expressed by following relation. Okay. So, the first Pala-Kirchhoff stress tensor is a function of the local value of the deformation gradient tensor as well as the current position of the particle, where the current position of the particle is there to allow for possible inhomogeneity of the material. So, if you have inhomogeneous response, then this particular term explicit dependence on the particle position helps. Okay. So, in the special case, when the work done by the stresses during a deformation process is dependent only on the initial state at time t0 and the final configuration at time t, okay, then the behavior of the material is said to be path independent and the material is referred to as hyperelastic or green elastic material. Okay. Suppose your work done by the stresses depends only on the current state and the initial state, and it does not depend on how you achieve the current state from the initial state, that is the response to the material is path independent, then such kind of materials are called the hyperelastic material or green elastic material. Okay. So, as a consequence of this, the stored energy, strain energy function or the elastic potential psi per unit the undeformed volume can be established as a work done by the stresses from the initial to the current position as psi equal to P double contracted with the rate of deformation gradient tensor integrated over time from initial time to the current time. So, the total strain energy that is stored inside the body is nothing but the strain energy density or the work done by the stresses from the initial configuration to the final configuration. Okay. So, psi here is the stored energy per unit undeformed volume. Okay. And now, this depends, psi depends on the current value of the deformation gradient and also the current position. Okay. So, we can identify the material time derivative of the stored strain energy density function psi dot as P double contracted with F dot. Okay. So, if you use this in this particular expression, the total stored strain energy, okay, per unit undeformed volume, okay, is given by integration of psi dot from initial to final configuration. Okay. Now, if you can somehow set up experiments, okay, to get this stored energy density function. Okay. So, you using some experiments, okay, you can determine the functional form of psi, for example. Okay. Then the rate of change of potential can be alternatively expressed as the work done by the stresses from the initial to the current position. Okay. So, psi dot, okay. So, psi dot will be nothing but, see, psi is a function of f. Okay. So, del psi by del t will be equal to del psi by del f contracted with del f by del t, and this is nothing but f dot and this is nothing but del psi by del f. So, in indicial notation I can write psi dot as summation over I n j del psi by del f I j f dot I j. Okay. So, this is the expression for the work done by the stresses from the initial to the current position. Okay. Now, the expression for the first parallel Kirchhoff stress tensor can now be written as P equal to del psi by del f into f dot. Okay. So, as a direct notation I can write P equal to del psi by del f, okay. Sorry, this will not be here, del psi by del f. Okay. So, this relation, equation number 5, is used as a definition of hyperelastic material. Okay. So, you can further develop equation 5 now using the objectivity constraints. This means that, what does objectivity constraint imply? This means that the stored strain energy density potential psi must remain invariant when the current configuration undergoes rigid body motion. Okay. For example, if there is rigid body rotation, then the psi must remain invariant. Okay. And how can this be ensured? This means that the psi, okay, you remember psi here, okay, if you see here, psi is a function of f. Okay. So, psi must depend on f, okay, that is given, but it can depend on f only through the stress tensor u, okay, and it must be independent of r, which is the rotation tensor. Remember, the using right polar decomposition, deformation gradient tensor f can be decomposed into one which is the rotation part and the another which is the stretch part. So, r corresponds to pure rotation and u corresponds to your stretch. Okay. Now, if the effect of rigid body motion or the rotations have to be taken away, then my psi has to depend on f through u. Okay. Okay. It cannot directly, psi cannot directly depend on f, it can depend on u, and u can only be obtained from f. So, in a way there is a relation between psi and f, but in between you have this stress tensor u, and then because psi depends on u, we have taken out the effect of rotation r. Okay. So, for convenience, however, psi is often expressed as a function of right Cauchy Green tensor C, which is given by u square, okay, which is nothing but f transpose f. Okay. So, our psi will be function of C and x, and C is a function of u and u is a function of f. Okay. But from this relation, C can be also be said as function of f. Okay. So, psi cannot directly depend on f, psi has to depend on say C or u, and then C depends on f. So, that is how this dependence of the strain energy density potential on the deformation gradient tensor is obtained. Okay. Therefore, psi, which is has to be a function of deformation gradient tensor, and the current position has to be a function of right Cauchy Green tensor, okay, and the current position. Okay. Now, we know that the material time derivative of the Green Lagrange strain tensor is twice the material time derivative of the right Cauchy Green tensor. Therefore, because the Green Lagrange strain tensor is work conjugate with the second Pavlov-Kirchhoff stress tensor, okay, we can totally write a Lagrangian constitutive equation, okay, in the same manner as equation 5. Okay. So, this was our equation 5, which was the constitutive relation for a hyperelastic material, okay, in terms of the first Pavlov-Kirchhoff stress tensor and the deformation gradient tensor. But P and F in equation 5 are 2-point tensor. So, a part of them also resides in the spatial configuration. To get a totally, okay, so to get a totally Lagrangian constitutive relation, what we can do is we can convert the, we can obtain a totally Lagrangian constitutive relations by converting the first Pavlov-Kirchhoff and the deformation gradient into second Pavlov-Kirchhoff and the Green Lagrange strain tensor. Okay. So, if you see the internal virtual work expression, that was integration of the work done by the second Pavlov-Kirchhoff and the Green-Lagrange strain tensor, work done by the second Pavlov-Kirchhoff stresses integrated over the material configuration. Okay. Now, if I substitute E dot as, so this is 1 by 2, okay, because E is 1 by 2 C minus I, therefore, E dot will be 1 by 2 C dot. Okay. So, instead of 2 here, we should have 1 by 2. Okay. So, E dot here, if I substitute 1 by C dot, I will get 1 by 2 S double contracted with variation of the material time derivative of Wright-Cauchy-Green tensor integrated over the material configuration. Okay. And this I can, the total internal virtual work will be the integration of the stored virtual strain energy over the reference configuration. Okay. So, psi dot is nothing but del psi by del C double contracted with C dot, and it is also will be equal to 1 by 2 S double contracted with C dot. Okay. So, if we equate both these, so psi dot is also equal to this and is equal to this. So, these two expressions have to be equal. So, del psi by del C double contracted with C dot minus 1 by 2 S double contracted with C dot should be equal to 0. So, because C dot is common, okay, in both the expression I can take it outside, and I get del psi by del C minus 1 by 2 S double contracted with C dot equal to 0, and this implies that S, and if this is equal to 0 for all C, then S or the second Pavlov-Kirchhoff stress tensor should be equal to twice of del psi by del C. Okay. And now, because E is 1 by 2 C, which means C is 2 E, and if I use this here, I can get the second Pavlov-Kirchhoff stress tensor as the derivative of the stored strain energy density potential with respect to the Green-Lagrange strain tensor. Okay. So, for hyperelastic material, the second Pavlov-Kirchhoff stress tensor can be obtained by taking the derivative of the stored strain energy density potential with respect to the Green-Lagrange strain tensor. Okay. Now, this relation between the second Pavlov-Kirchhoff stress tensor and the Wright-Cauchy-Green tensor C will be a nonlinear expression. Okay. So, when we come to our Neo-Hookean model, you will see that psi is a nonlinear function in C or E. Okay. Now, if it is a nonlinear function in C, you will get a nonlinear relation between the second Pavlov-Kirchhoff stress tensor and the Wright-Cauchy-Green tensor. Okay. And when you have to set up the Newton-Raphson solution process for studying the deformation of a hyperelastic material under external loads, you have to linearize this relation between the second Pavlov-Kirchhoff stress tensor and the Wright-Cauchy-Green tensor. Okay. And this has to be linearized with respect to an increment u, which is usually the displacement in the current spatial configuration. Okay. So, this means you have to take the directional derivative of the second Pavlov-Kirchhoff stress tensor in the direction of displacement u. And how can you do this? You can use the chain rule. So, the directional derivative of the second Pavlov-Kirchhoff stress tensor in the direction of u. Okay. What it actually means is, if you have a small change in the current configuration, okay, given by u, then what is the change in the stresses? Okay. So, this change in the stress by this much change in the displacement from the current configuration is nothing but the directional derivative, and the way you can compute is d by d eta of this first Pollack-Kirchhoff stress tensor, which is a function of Green-Lagrange strain tensor, which in turn is a function of the current configuration plus your eta times u. Okay. So, the directional derivative, and now you can use the chain rule. S depends on Green-Lagrange strain tensor and Green-Lagrange depends on u. Okay. So, d by d eta of S is nothing but d by dE of S double contracted with d by d eta of the Green-Lagrange strain tensor evaluated at the configuration phi plus eta u. Remember, phi is same as psi. Okay. I am using phi here because psi is used here for the strain energy density potential. Okay. So, to remove that confusion, I am using phi here. Okay. So, now if you look closely, this relation, okay, this expression over here is nothing but the directional derivative of the Green-Lagrange strain tensor in the direction of displacement u. Okay. So, using this, I can write the directional derivative of the second Pollack-Kirchhoff stress tensor in the direction u is nothing but del S by del E double contracted with the directional derivative of the Green-Lagrange strain tensor in the direction u. Now, I can denote del S by del E by a symbol C, okay, and then the directional derivative of S in the direction u is C double contraction with directional derivative of Green-Lagrange strain tensor in the direction u. And we know the relation between the directional derivative and the material time derivative. Okay. So, they are one and the same. So, directional derivative of S in the direction of velocity v will be nothing but the material time derivative S dot. Okay. So, I can write this expression instead of u, if you take the velocity v, then I get the material time derivative of the second Pollack-Kirchhoff stress tensor is C double contracted with the material time derivative of Green-Lagrange strain tensor. Okay. Now, since directional derivative of S and the directional derivative of E, these both are second order, okay, they both are second order tensors. Therefore, this quantity, okay, C is a fourth order symmetric tensor, okay, because both S and E are symmetric tensor. This you will remember from our kinematics discussion. So, because both S and E are symmetric and they are second order, therefore, C has to be a fourth order symmetric tensor, and it is also called the material or the Lagrangian elasticity tensor. Okay. So, this Lagrangian or the material elasticity tensor, which because it is a fourth order tensor, it can be expressed in terms of its basis, okay, and because both S and E are in the original configuration or the undeformed configuration, therefore, we use the basis in the undeformed configuration, which is given by capital E. Okay. So, C will be summation over I j k l C I j k l E I tensor product E j tensor product E k tensor product E l. So, what will be C I j k l? Okay. C I j k l you can obtain, and when we are discussing how to get the components of a fourth order tensor, this can be obtained by taking the double contraction of C with respect to E k E l, E k tensor product E l, and then taking the double contraction of the resulting second order tensor with E I tensor product E j. More precisely, C I j k l, okay, is nothing but del S I j by del E k l. Okay. This is a direct notation, okay. And because E is 1 by 2 C, okay, therefore, the material elasticity tensor C is also written as twice of del S by del C. Okay. And now, because S is del psi by del C, if I substitute this here, what I get? The material elasticity tensor is 4 times of, so this is twice. So, 4 times of del square psi by del C del C, okay, or C I j K L is nothing but 4 del square psi del C I j del C K L. Okay. So, this is the direct notation and this is the indicial notation. So, you can determine the material or the Lagrangian elasticity tensor C if you know the functional form of psi, and psi depends on C, okay, and the current position x if it is heterogeneous material. Therefore, if you know this relation, it should be possible for you to get the expression for S if you take del psi by del C, and to study the response of the material you need the fourth order elasticity tensor C, and which you can obtain by 4 times of del square psi by del C del C. Okay. So, given psi, both the second Pavlov-Kirchhoff stress tensor and the Lagrangian material elasticity tensor can be known. Okay. Now, because C or the material elasticity tensor is a fourth order tensor, the transformation relation is given by C dash I j k l is q m I, q n j, q o k, q p l, c m n o p. Okay. So, there are 4 transformation tensors Q 1, 2, 3, 4. Okay. And the another point to note, okay, if you see this relation over here, okay, so I will rub first of all this. If you see this relation over here, if I just interchange I j and k l, I make this k l and make this as I j. So, on the left hand side it becomes k l I j. Okay. So, the result will not change. Okay. So, you will get the same expression for the material constitutive tensor. So, this is called the major symmetry, and because both, okay, so C I j k l is del S I j by del E k l, because S is a symmetric tensor. So, if I replace I j by j I can get C j I k l as del S j I by del E k l, and because S is symmetric, S j I is same as S I j. So, what I see is C I j k l is same as C j I k l. Similarly, because strain is symmetric, I can show that C I j k l is same as C I j l k. So, these two, okay. So, the order of differentiation does not matter, implies you have what is called the major symmetry. C I j k l is C k l I j. The symmetry of the second Pavlov-Kirchhoff stress tensor implies what is the minor symmetry. C I j k l is C j I k l, and the symmetry of the strain implies, okay, that C I j k l is C I j l k, okay, because S I j is same as S j I and E k l is same as E l k. Okay. So, these are called the minor symmetry and this is called the major symmetry. Okay. Thank you.